Okay, let's go ahead and get started. It's actually a little slow. All right, so as you can probably tell from what's up on the board, today's topic is going to be K-maps. K is short for Karnaugh. Okay, so Karnaugh maps. And the purpose of Karnaugh maps is to reduce Boolean expressions. So last class, when we were writing the SOP and the POS equations from the truth table, those were non-reduced. Okay. And you can reduce Boolean expressions as you do base 10, where you like factor common terms out and like combine things. If you look at this handout that I had on each table last time, towards the bottom, there's these laws and identities. And you would see that some of these are just like base 10. For example, like the order when you OR variables together doesn't matter. Like X or Y is the same as Y or X. Okay, just when you do addition in base 10. And there's other similar laws to base 10 if you look at these. Now, De Morgan's, you don't have a De Morgan's in base 10. De Morgan's is specifically base 2. Okay, but a lot of these other laws and identities are similar or the same as really base 10. So, you couldn't use these laws and identities in just like a base 10 algebra equation that you do, factor out and combine like things, stuff like that. You could do it that way. But Karnaugh maps is a pictorial way of reducing Boolean expression. And at least some people find Karnaugh maps fun. Okay, I'm not like saying it's the funnest thing in the world, but at least I think it's funner than, doing the brute force way or, like you would have base 10 a question. So anyway, that's the purpose of Karnaugh maps. And, we're going to go over the basics of Karnaugh maps. And then I got a bunch of examples. And the activity is Karnaugh maps. And then part of lab 1 that you can start today is involves Karnaugh maps. Okay, so Karnaugh maps, all kinds of Karnaugh maps. But before we start Karnaugh maps, there's just a couple of other things I want to go over. The first thing is, this is inequality. Okay, this not A ANDed with not B. It's not equal to A and B ANDed together and then the whole thing not. Okay, so I want to ask you, like, why is this an inequality? Like, why isn't that those two things equal? Because what kind of gate is this? That's an AND gate, right? Because A and B are being ANDed together, and then the whole thing's being NOTed, right? That's an AND gate. So when we talked about De Morgan's last class, what did we say a NAND gate is equivalent to? What does De Morgan say? One part of De Morgan's tells us that a NAND gate is equivalent to a OR gate with inverted. Yeah, exactly. A NAND, right, from De Morgan's, right? Remember, there's two parts to De Morgan's, but one part of De Morgan's tells us that a NAND is equivalent to an OR gate with inverted inputs, not an AND gate with inverted inputs. Okay, so due to De Morgan's, we know this is not true. And you see, the reason I mention this is because this is a common error. Okay, a common error is that say you're writing either an SOP or POS equation, from a truth table, and say your term is A, not B, not C. Well, an error that people make is they'll do this. Because these two knots are close together, sometimes they connect. Okay, but that's not the same. See, these are not equivalent. Okay, now I think sometimes it happens just because you kind of knot both and one knot runs into the other knot and they kind of connect. You didn't mean it, but it just happened. Well, watch out for that because on work that you pass in, especially like on a midterm, if you meant this, but you wrote this, it's still wrong. Okay, so you just got to be careful with your bars. Okay. All right, the next thing is that there's two other ways of representing logic. You know, we talked about like a truth table, and you know, circuit diagram and Verilog code last time, right? We talked about all those various forms. Well, here's two forms that I didn't talk about last time, and the only reason I'm bringing it up today is because on the activity, and the activity is on each table, and there should be enough for everybody at the table. If there isn't, let me know and I'll get you another one. But on this activity, it has these two other forms, compact min and compact max. Okay, now compact min, it has this sigma symbol, and then in parentheses, it has numbers. Okay. Compact max, it has this capital pi symbol, and again, in parentheses, some numbers. Well, when there's a sigma, okay, when we have compact min and there's a sigma, these numbers correspond to the ones in a truth table. And when you have the capital pi, compact max, these numbers tell you where the zeros are in the truth table. Okay, so that's why they're called compact, because this is a shorter way of writing where the ones and the zeros are in a truth table. Okay, so here, the compact min, since it only goes up to 6, I wrote a truth table with 3 inputs, right? Because with 3 inputs, we can go 0 to 7. So if I now look at this compact min expression here, I can fill out the truth table because these numbers tell me where the ones are. So there's a 1 when the input is 0. There's a 1 when the input is 1. There's a 1 when we have a 5, and there's a 1 when we have a 6. And all the other outputs would just be 0. Okay? And then here, since the numbers go up to 15, right? That would be a truth table with 4 inputs, right? Because with 4 inputs, we can go 0 to 15. So filling out this truth table, looking at this compact max, I would have a 0 for input 3, a 0 for input 7, a 0 for input 8, and a 0 for input 15, and then all the rest would be 1. Just fill out the rest with all ones. Okay? So that's all this is about. Again, the only reason I really bring these up is because they're on that activity index. Okay, so any question on why this is not equal, or compact min or compact max? All good?
So compact max shows the zeros and compact min tells you the ones.
Yeah, okay. Yeah, that's all it is. Okay, so let's go ahead now and start talking about K-maps. So here in this class, we either will have an 8-cell K-map or a 16-cell K-map. And each cell is numbered, and we call the number an index. And you can see the numbers go 0, 1, 3, 2, 4, 5, 7, 6 for the 8-cell. For the 16-cell, it's the same, the first 2 rows as the 2 rows for the 8-cell, but then it goes 12, 13, 15, 14, and 8, 9, 11, 10. So the first question people normally have when they look at a K-map is, why are these numbers, these indexes, why are they not in sequence? Like, why isn't this 0, 1, 2, 3, 4, 5, 6, 7? You know, why are they out of order? Okay, well, the reason why they're out of order is because when the cells are numbered like you see, we have the property called unit distance. And what unit distance means is that if you look at any cell and compare it to a cell to the left or the right or above it or below it, there's only a 1-bit difference between those two binary numbers for that index. So for example, if we were to look here at cell 1 and then compare it to this cell that's next to it, the index of the cell next to it, 0. So look, here's 1 and here's 0. See there how there's only a 1-bit difference? If I compare 1 to 5, 1 to 5, See how there's only a 1-bit difference? If I compare 1 to 3, 1 to 3, again, there's only a 1-bit difference. Okay, and that's true of any cell you look at. If you look and compare it to the cell to the right, the cell to the left, or the cell up, or the cell down, you're only going to see a 1-bit difference. Okay, see if we had numbered it like this, right? If we had put, 0, 1, 2, 3. Well, now when I compare cell 1 to cell 2, look, that's a 2-bit difference. That's not unit distance. Right? So you see, that's why it's not in order. And you have to have unit distance between cells that, again, are either left, right, or up, down, in order for K-maps to work. Okay? In order for K-maps to give you a reduced expression, you have to have that property. Right? If we didn't have the unit distance property, everything I'm going to show you today would not work.
Really sorry, I don't want it to say I don't get it. That's not very useful feedback. I don't get.
Okay. Well, let me just back up. When we compare these two, okay, again, say we're looking at this cell, right, which is number 1, and we compare it to this cell that's right next to it. What we're comparing are the indexes, which are just the binary numbers of the inputs. So if I'm just looking at these two binary numbers, can you see there's only a 1-bit difference? Right? To see how these are both 0, these are both 0, but this is 0, this is 1. Also, if I compare 1 and 3, right? So if I compare 1 and 3, also there's only a 1-bit difference. Okay, and then also with 1 and 5, see 1 and 5, 1-bit difference. Okay, so that's because I put this out of order, right? If I put this in order, and now I do the same thing. I'm comparing 1 to all the cells, to the left, right, and below. Now, of course, this is still going to be okay. 1-bit difference. This is going to be 1. But now, if I'm comparing 1 to 2, there's a 2-bit difference. So that is not unit distance. Okay, unit distance just means that there's a 1-bit difference between the two binary numbers. And like I said, you have to have that property in order for K-maps to work. In order for K-maps to give us a reduced expression, the map has to have that property. Now, the reason for that, there's like a whole mathematical proof, which, I think I saw when I was a graduate student, and that's the last time I saw it. Another thing I should probably mention at this point is that, even though, we're teaching you, or, I'm teaching you Carnot maps, if you go work out in industry, I'll get to your question in a second. If you go out and work in industry, you're not going to use this, and you're also not going to use the brute force method to reduce Boolean expressions. There's going to be computer programs that will do it for you. But at the very least, having knowledge of Carnot maps, and even just having this knowledge of unit distance, algorithms are based on it. So it would give you an understanding of, the actual algorithm that would be used in the program that you get your reduced expressions from. Let me take this question first, and then come to you.
So in your example, you stated a 1-bit difference for each one, and I'm assuming looking at those maps, that could also be a 0-bit difference as well, either 1 or 0 for each one around it, or is it always 1?
Are you talking about like what's inside the squares, the cells?
Yes, how you really use. So
Well,
that completely unrelated, you wouldn't write the 1 and the 1.
well, we're going to get to this, but
Okay.
what's written inside a cell is the output that goes with that input.
Okay.
Yeah, so it doesn't have anything to do with unit distance.
Okay, I thought you were writing the 1 bit inside the box.
Okay. Yeah.
So I don't really understand what you mean by like bit difference. I don't understand how you're deriving that.
Oh, all I mean by bit difference is that when I look at these two binary numbers, I'm just seeing how many bits are different between these two, right? These are the same, right? They're both 0. These are both 0, but this one is 0 here and 1 here. So that's a 1-bit difference. Compared to if I compare binary 1 to binary 2, there's only 1 bit that's the same and 2 bits are different. That's all I mean by 1 bit and 2 bit. Okay? I mean, if you compare like 0 to 7, that's a 3-bit difference.
Okay.
That's all. Yeah. All right, sure. Yeah, also this unit distance, it's part of what's called adjacent theory. All right, I'll just leave it at that. Like I said, there's a whole mathematical proof. I mean, this was something that, a mathematician a long time ago, I think like in the 1700s came up with, and then they applied it to digital when, the digital revolution happened. Okay, so that's that. Now, the next thing that people often wonder about is when they're looking at a Carnot map is, okay, why is there an A here? Why is there a C here? Why is there a B? And so on. All right, the reason why you see an A for this row is because if you look at 4, 5, 6, and 7 in the truth table, 4, 5, 6, and 7, see? A is 1 for all those numbers, those indexes. Likewise, 0, 1, 2, 3, if you look at 0, 1, 2, 3, A is 0 for those binary numbers. So you could also write not A next to that row. Okay, the reason you see B in this line here means that B is these 2 columns. And the reason you see a B there is because if you look at 2, 3, 6, and 7, so 2, 3, 6, and 7, that's where B equals 1. So that means these 2 columns would be not B, right? Because if you look at 0, 1, 4, and 5, right? 0, 1, 4, and 5, B is 0 for those. Okay, likewise, these numbers here, 1, 3, 5, and 7 for C is 1. See, here's 1, here's 3, here's 5, here's 7. So this column would be not C, and this column would be C. Right, so does everybody see what I did there? And it's the same concept when you get to a 16th cell. The reason why these 2 rows have A is because for all these numbers, 8 through 15, A is 1. Then for these 2 rows, you'd have not A, because for all these numbers, A is 0. Okay, for all these numbers, C is 1. So these columns over here would be not C. For these 2 rows, B is 1. So this row would be not B. This row would be not B. For these 2 columns, D is equal to 1. So this column would be not D, and this column. Okay, usually the not variables are not shown. Usually they show just the A, B, C, but it's understood what the other rows and columns. Okay, does that make sense? All right, so now how do you fill a Carnot map? Well, as was mentioned a little while ago in response to a question, what goes in the cells is the output that corresponds to that input, corresponds to that index. So if I'm going to fill this K-map with this truth table, well, in cell 0 goes a 1. And that's the output for input 0. In cell 1 will go a 1. In cell 2 would be a 0. In cell 3 would be a 0. In cell 4 would be a 0. In cell 5 a 1. In cell 6 a 1. And in cell 7. I am just filling the cells with the output that corresponds to that index, that input. Okay, and then likewise, it is 16 cell. Now, remember, we only have 4 zeros here, right? There's a 0 for 3, right? Index 3, for 7, 8, and 15. And then all the rest would be 1s. Okay. So everybody could fill in a K-map from the truth table. All right, so now we can start actually using a K-map to reduce or get reduced expressions. So the goal when you're using a K-map is to get the least number of largest groupings. So you're gonna see that we're gonna start grouping either ones or zeros. Okay, you can group either ones or you can group zeros, just like you can write expressions from a truth table either by looking at the ones or looking at the zero that we did last. Okay. Now, these groupings, they have to be square or rectangular. Okay, you can't have like diagonal groupings. You can't have irregular shape groupings. Okay, it can only be square or rectangular groupings. And whether you're grouping ones or zeros, those groupings can only be 1, 2, 4, 8, or 16. Okay, you can't have groupings of 3, can't have groupings of 6, or any other number other than 1, 2, 4, 8, and 16. Okay. Now you're going to see why this is true when we start doing some examples. But if you have an 8-cell K-map and you do a single grouping, right? You just group 1, 0, or 1. That's going to give you a 3-variable term. If you have an 8-cell and you do a grouping of 2, that's going to give you a 2-variable term. If you do a grouping of 4, it's going to give you a 1-variable term. If you do a group of 8, when you have an 8-cell, so that means like either all cells are 1 or all cells are 0. And remember, what goes in the cell is the output value. Well, if you have all 1s, that means the output's always 1. So F would just equal 1. And if all your cells were 0, well, your output would always be 0 and F would just equal 0. Okay, so if you have 8 1s, well, then the answer is just, well, the output equals 1, because it's 1 all the time. Or if you have 8 zeros, it would just be F equals 0. And then, of course, 16 doesn't apply to an 8-cell. We only have 8 cells. All right, for a 16-cell, if you have a single grouping, you get a 4-variable term. If you have a grouping of 2 with a 16-cell, it'll give you 3 variables. 4 will give you 2 variables. 8 will give you 1 variable. And if it's 16, it's either equal to 1 or equal to 0. Right? Because all the cells will be that value. Okay, now you're going to see why this is true. Okay, when we go through the examples. All right, but this was all the preliminary, and now I got to move the camera. I remembered to move the camera today. I also remembered to start the recording, so 2 for 2. Let's see, I think we can go way over here. And point it this way. Okay, that looks good. All right, so you can see I have a bunch of examples up here, and I didn't pick these examples like haphazardly, like I just didn't do this to give you busy work. Okay, I picked all these examples for a reason, because each example, you know, something like new comes out. Okay, and we're going to start, you know, anything that's new is challenging, I know, but we're going to start out not so challenging and, you know, get more challenging as we go. Okay, so we're going to start with this K-map here. And again, for any K-map, you can group either ones or zeros. Now, think about back last class when we were looking at a truth table, we were getting the non-reduced, right? The non-reduced expressions. If I'm looking at a truth table and I look at the ones, right? I write my SOP for where the ones are in the truth table. What kind of expression am I getting? Directly from the truth table. What did we do last time? Right, because I took, you know, this input or this input or this input or this input. What kind of equation is that? Say it again. SOP, right? Sum of products. It would be sum of products for, since I'm looking at ones, what would be, like I have my sum of products and it's equal to F, right? Because I'm looking at the ones. And then if I look at the zeros, I get sum of products for F naught. And one of the reasons you might want to get SOP for F naught is because if I do De Morgan's twice, I get POS for F, right? Well, it's the same thing with Karnaugh maps, except Karnaugh maps is gonna give us the reduced SOP. So if I want the reduced SOP for F, I circle or group ones. And if I want to get the reduced POS for F, I would look at the zeros because I would want to get the reduced SOP for not F, right? Before I do the De Morgan's twice and you get the POS. Okay, so you know what you learned previously when we were just looking at truth tables still applies to when you're looking at a Karnaugh map. The only difference is a Karnaugh map is going to give you a reduced expression, where looking at the truth table doesn't give you a reduced expression, right? Just give you a non-reduced. Okay. All right. So we're going to group ones. All right. So that's going to give us an SOP for F. Okay. So remember, we want the least number of largest grouping. So when I do Karnaugh maps, this is how my mind thinks. I'm thinking, okay, do we have a group of 8? Well, clearly we don't have a group of 8 ones because there's only 3 in the map. All right, well, do we have a group of 4 ones? Well, no, that's not possible again because we only have 3 ones. Okay, and I'm just going down the list. You know, I look for 8, I look for 4, now I look for 2. Do we have a grouping of 2 ones here? Do you see? Yeah, what cells? Yeah, 0 and 4, right? Because again, these groupings, they can be square or rectangular. This is a rectangle, right? Okay. So now to get the term, okay, to get the term for that grouping, you look at what's common to that grouping. So you're looking at this grouping and what's common, what variables are common? What is it? Okay, not C is common. Is that the only one? And not B, right? See how this 2 grouping, because remember, right? These 2 columns are B, so these 2 columns are not B. And then this is not C, this is not C. So this 2 grouping, not B and not C are common. See, the one that changes is A. Right? Because this one is in the A row, this one is in the not A row. See, whatever variable changes, that drops out. That's not in the term. Okay? So you see, this 2 grouping would give us not B, not C. Does everybody see how I got that? Okay? All right, now we're not done because we got this other one over here. You got to make sure that whatever you're grouping, you know, that one in this, you know, these ones in this case have to at least be part of one group. So we're going to have another term. So now we have an or. And can we group this one with anything? Nope, it's all by itself. Okay, so what term are we going to get for this single grouping? What's common to that single grouping? Okay, B. Not A. Not A. C also. And C also, yeah, you're going to get a 3 variable term. See, when it's a single grouping, you're just writing the index. So yeah, it's going to be not A, B, C. Right, just like you're writing a 3. All right, so you see, this would be the reduced SOP for F. So any questions on that?
So step 1, group ones, step 2, variables, find the variables in common, the group 1 group, and then what's the last step that you said? To get the not A, B, C.
Yeah, see this, not B, not C, that's coming from the 2 grouping, because that's, those 2 are common to that 2 grouping. The not A, B, C, it's coming from this single grouping, right? Because it's in the not A row.
Oh, and then you get the
Right, yeah. Okay. All right, let's do another one. Let's do this next one. And again, we're going to group ones. Okay, now the reason I have this example is because the edges of the Karnaugh map touch. So, you know, you kind of think of this as a cylinder, and like you cut the cylinder and then you make it flat. So these edges touch. Okay, these cells touch. So knowing that those edges touch, how would you group those ones? Again, you want the least number of largest groupings.
So you should group the four.
That's it, yeah, because they touch. We have a 4 grouping of 0, 4, 2, 6. Okay, and it's gonna be F. And then what's common to that 4 grouping? It's not C, right? It's all of the 4 1 are in the not C column, right? A changes and B changes. So that those drop out. So this is just equal to not C. So can you see now why least number of largest groupings? Because if you had, instead of grouping these 4 together, like is the correct answer, if you had instead done a 2 grouping here and a 2 grouping here, how many terms are we going to get if we have two groupings? How many? 2, because each group gives you a term. And then how many variables is each of those terms going to have? 2, right? So that's why it's the least number of largest groupings, because the least number gives you the minimum number of terms, and the largest groupings gives you the minimum number of variables, right? That's the most reduced. Does that make sense? Okay, so that, like I said, every time you do increment, that's what you got to be thinking. I want the most reduced, so I want the least number of largest groupings. And again, the groupings can only be 1, 2, 4, 8, 16, and they got to bring rectangular or square.
So in like, so if cell 6 was a 0, is that like
Okay, so you're saying in this example here, this was a 0 instead of a 1?
yeah, instead of having your 4 group, it still work the same way, it's touching the edge, that's still a group.
Okay, well, remember though, you can't have a 3 grouping. The groupings either have to be 1, 2, 4, 8, or 16. Yeah. So yeah, if this was a 0, you would have to go with two groupings.
Okay.
Yeah. Okay. All right, let's look at the next one. Again, we're going to group 1.
They said 2 group was only, so that one was a 0, then edge would be 12, 0, 1 would be, you're like.
Well, yeah, actually, tell you what, let's do this one. We'll come back to this one.
Okay.
Because actually what you're asking is the reason I have this. Okay, I'll come back to this after we do this. Okay, so let's do this. That's ones. All right, so we want to group ones. So it's going to be F. So what would you group first? Again, it's good to always group the largest groupings first. Yeah, right here, this 4 grouping, right? So this 4 grouping here that has 1, 3, 5, 7. So what term is this going to give us? What's common to those 2? Just C, right? Okay, now the reason I came up, or I used this example, is because now we got to take care of this one over here. And you can overlap groups. So since I can overlap groups, how would I group this? 7 and 6. Okay, so that's why I wanted to wait, because if this is a 0, you could do like this 2 grouping and then this 2 grouping, because you can overlap. Yeah. Okay, so yeah, we would do the. And then what term are we going to get from this 2 grouping? What's common to these 2? Right. AB. Now, even though order doesn't matter, right? You can write BA, that's the same as AB, but by convention and also just for ease of reading, please put these in alphabetical order. Okay, like I've been doing, especially when someone's grading, it's just easier. Okay. Again, it's not wrong. I mean, if you put C or BA, that's the same as C or AB, because order doesn't matter. But again, just for readability, please put them in alphabetical order. All right, the next one, let's group zeros. So since I'm grouping zeros, I'm gonna get SOP for what? Not out. Not. Okay, just like when you take zeros from the truth table, right? You're getting an SOP for not out. The only difference, non-reduced from the truth table, reduced from the table. All right, so we're grouping zeros. So how are you gonna group these? Can we do this? Could we do a group of 4 like this? No, because that's an irregular shape. Yeah, it's gotta be square or rectangular.
Yes, individually.
Say that again?
Not do them individually.
Well, when you, oh, you mean single groupings? All single groupings?
Oh, wait, no, with the two, like with the two.
Yeah, yeah, we can do, where do you want to do a
Oh,
group of
wait,
2?
we could do,
Well, give me one group of 2.
the not A and not B.
Well, give me the cells and then we'll get the term from that.
0, 1.
Okay, yeah,
Sorry.
yeah. That's all right. So you can do a grouping here. And what term would that give us?
Not A, not B.
Yes, right, because they're both in the not A row and the not B column. Yeah, this would be not A, not. All right, what else would you do?
0, 2.
Okay, could you 0 and 2? Because again, these edges touch. So what would that grouping give us?
Not A, and not C.
Yep, not A and not C, right? And then what's left?
5, 7.
Okay, 5 and 7. Okay, and what term would that give us? It's AC, right? Because they're both in the A row, C column. Now, the reason why I picked this example is because there's more than one correct answer for this. Because can you see how we could have done a different grouping?
1, 2, 5, 5.
Yeah, you could do the 1 and 5.
5, 7.
Yeah, you could do the 1 and 5, 5 and 7, and still have the 0 and 2, and that would give you 3 terms that are 2 variable each. So this example, there's 2 equations that are equally reduced. So in a case like that, either one of those is correct. Now, what you don't want to do is you don't want to do what we did here to get this expression, and then also do another grouping of 1 and 5, because that would add a redundant term, right? Because once you've covered all the zeros in this case, whatever you're circling, once you've covered all those zeros at least once, you're good. All right, so you see, if you were to do after getting this expression here, doing these groupings that we just went over, if you did another 2 grouping with the 1 and 5 that gave you another term, that would not be the most reduced.
I just want to verify something. So connected 2 and 0 together, is it also valid to connect 6 and 4 together? Like,
Well,
so I'm not, so,
Well, you mean if we were grouping ones?
yes, yeah,
Yeah.
I just want to understand how the edges are.
Yeah, that, this entire edge touches. So we did it up here, right? Because we made this group of 4, 4 and 6 were touching along with 0 and 2.
Oh, that's when you did that. And then what about, for the larger grids that are all the sides connected?
Oh, when we get the 16 cell?
Yeah,
Yeah, I'll talk about that.
Okay.
Yeah, it's coming up.
Cool.
But yeah,
I'm not
you're thinking the right way. Yeah.
okay.
Okay, other questions at this point?
Would it still happen, so do 0, 1, 5, and 7, and then 0, 1, 2? Or are you talking about the least number of vehicles?
Okay, so you're saying if you did 0 and 1, 5 and 7, but then just 0 by or 2 by itself?
If you did 8 on the
Or if you just did a single? Yeah, see, that wouldn't be as reduced, right? Because that, either way, you got three terms. But if you just have this as a single, one of your terms is three variables instead of two. So yeah, that wouldn't be most reduced, yeah. Yeah, I mean, your question's a good question because again, it points this out. Least number of largest groupings. Yeah. Okay. All right, let's do this one here. And we're gonna group one. And what's different in this K-map? What's in this K-map that you haven't seen yet in this class? Dash. Yeah, there's a dash here, and a dash here. Well, when you have a dash, and remember what goes inside the cells of the K-map are the outputs, right? So we're saying that, you know, these two outputs for these two indexes, these two inputs is a dash. Well, what a dash means is don't care, doesn't matter in any of these. Irrelevant. Who's a good speller? Irrelevant. Is there an E then B-A-N-T or is it something else? Okay. For some reason that doesn't look that way. All right. But anyway, a dash means don't care, doesn't matter, irrelevant. So the dash, it's either a 0 or a 1 because, you know, this K-map's representing some digital circuit, just like a truth table is. And again, a digital circuit, the values are binary. It's either 0 or 1. There's no like third value, right? So a don't care means that it's either a 0 or 1, but we don't care. The most common example in an actual circuit of an output that you don't care about is an output that's not connected. Okay. You know, you'll see that often digital devices and you know, some circuits, they have multiple outputs, but you're not always using all those outputs, you know? You might have an application where you're only using 4 of the 5 outputs. All right, so that 5th output would be a don't care. So you could make it a 0 or 1. It's not gonna matter to you. Well, when you're doing a K-map and you have a don't care, it's sort of like a wild output or wild card, if you will. Because you make the don't care equal to whatever will give you the most reduced expression. So you can make the don't cares either a 0 or a 1, but you pick the value that's going to give you the most reduced expression. Okay, so what values would you pick for these don't cares? Now remember, we're grouping ones. So if we're grouping one, what would you make these don't cares equal to get the most reduced expression?
4, 1, 6.
Yeah, I'd make this one a 1 and this one a 0. Because if I do that, I just have one single 4 grouping. Okay, so F would just be what would F equal for that 4 grouping? What's common for that 4 grouping?
A not B. Or it's not B.
Yeah, just not B, right? Because this 4 grouping is in the not B column. It is not. Okay, so does everybody see why we would make the don't cares equal to that? Because, you know, if you made this don't care 0, you'd have two groupings. That's 2 terms. Each grouping is 2 variables. That's a lot more than just a single variable, right? You know, and you know, you certainly wouldn't put a 1 over here, right? Because that would add a whole nother term. Okay. All right. How about for this one here? Let's see. We'll group zeros. Okay, and also we've got some don't cares. So first, what would you make the don't cares equal to get the most reduced expression? Grouping zeros. So since we're grouping zeros, this would be
Make them all 1.
yeah, make them all 1, right? If you make them all 1, you're just left with a single grouping of 2. See, I chose this one on purpose because I think sometimes when you have don't care like this, people think you have to make the don't care such that you use it, you know. But again, you make the don't care whatever you need to get the most reduced expression, right? So we want all these to be ones, because if any of them are zeros, it's gonna add to our expression, not take away, right? So what would not be, what term would we get for this two grouping? Not AC. Okay, so any questions up to this point? Because, well, go ahead, question.
One, 0, 1, 4, and 5. Then what if we make 2 and 6 ones at the most?
All right, so you're talking about this one here? And you're saying this would still be 1, 1, 1, 1, but now you put two ones here?
Actually, why can't it be 6? Because it's still a rectangle.
Right, but yeah. It's only these groupings that are allowed. Yeah, you can see they're like powers of 2, right? 2 to 0, 2 to 2, 2, 2 to 0, 2 to 1, 2 to 2, 2 to 3, 2 to 4. Yeah, so it's got to be a grouping of a whole number power of 2. But since you brought it up, I mean, if these two were ones, how would you group them? Yeah. Again, the edges touch, so 2, 6, 0, 4 would be a 4 group. Because again, you can overlap. Okay. Any other questions before we move on to 16 cell? Because I mean, if you understood these 8 cell examples, 16 cell, same concept. It's just now a single grouping gives you a 4 variable term, 2 grouping 3 variable, 4 grouping 2 variable, 8 1 variable, and then again, if you got all ones or all zeros, the output is just equal to that. All right, so let's look at this 16 cell, and we're going to group ones. So this is our path. So we're looking at this here. So what would you do first? Yeah, it's always good to start with the largest groupings first. 6. Right, exactly. Yeah. Again, edges cut now. Also, in response to an earlier question, with the 16 cells, you know, these edges touch and also the top and bottom touch. So it's sort of like a sphere and cut it and lay it out, you know, like a flat map of the world kind of thing. But yeah, this 412, 614, got a 4 grouping. So what term is that 4 grouping going to give us? What's common to that 4 grouping? Is it just B?
Oh, and not B.
Okay, this 4 grouping here. Let's see, they're both in the B row.
And not B.
Yeah, not D. Yeah, not D column. Okay, so B, not. All right, so what would you do next? 4 and 5, right? We'd overlap, make this a 2 group. And what term is this 2 grouping going to give us? What's common to this 2 grouping? B, right? And it's going to be a 3 variable term. So it's going to be B. And then what'd you say? Oh, wait, let me put the not A. Yeah, so not A, B, and what? Not C. All right, and then we just left with this. Can we do anything with that? It's just a single, right? There's no other one to group it with. So this would just be a single. So how many variables? 4. It would just be the index for 3. So it'd just be not A, not B, C, D. Okay. So any questions on that one? All right, let's go to this one. Okay, let's group some ones here. You get F. Now this example is somewhat similar to one of the K-maps you're going to have to do for lab 1. Okay, it's not exact, but it's somewhat similar.
That group of 4 and just the 2 groups.
Okay, so what group of 4 do you want to do first?
That third row.
Okay, so this row, yeah, that's a group of four.
And then you just do a second round, fourth round.
Okay, let's do the term first, and then we'll come back, okay? So what term is this gonna be? What's common to this four group?
I was gonna say, there's a more efficient way to do it, I think.
Okay, well, let's, let's go on, let's go,
Sorry.
all right, but anyway, what would we get from this four group? AB, right, because this four grouping is in the A row and the B row. All right, what do you want to do next? Well, give me the cell numbers, Bob said. Okay, you just want to do this two grouping? Does anyone see something else or have another suggestion? What cells? Yeah, you see, you would want to overlap, right? Remember, you could overlap. Right, because 5, 7, 13, and 15, that's going to give us less variables than just 5 and 7. Okay, so yeah, always remember you can overlap. Okay, so what term would we get from this four grouping? What's common to this four grouping? E and D. Okay. And how would you take care of these two?
That is 9, 11, 12, 14, are they all? Is that a group or like, said it was like all those sides, we just side.
Oh, what touches? It's these edges that touch, and then they, top and bottom touch. It's like a sphere, like a globe, and then you kind of cut it and lay it flat, like
Okay.
a flat map. Yeah.
Then 15, 12,
Say it again.
13, 15,
Yeah.
11.
Yeah, so we can take these two and overlap it with these two and make another group of four. So we end up with 3 groups of 4. Okay, so what term are we gonna get from this? What's common to this 4 grouping? AD, yeah.
So while we do have to be in 1, 2, 4, 8, or 6 for the grouping, do we always want the biggest grouping that we can get
Yeah,
to get the most simple?
yeah, exactly, because, that's the key thing, right? Because the largest group is gonna give us the least number of variables.
Yeah,
The least number of groups gives us the least number of terms. That makes it the most reduced. Yeah, no, that's how you gotta be thinking. Yeah, exactly. Yeah. Good. All right, let's do this one here. Let's group ones again here. Group ones. It's gonna be F. Okay, we got a don't pair. So first of all, what would you make that don't pair equal to? Right, because if I make this a 1, I can then do what? Yeah, we can do this 4 grouping. And that will give us, what do we get before BD? Okay, so now comes the reason why I have this example. Notice the corners are all 1. The corners touch, right? Because the edges touch and the top and bottom touch, and it's kind of like a sphere. When you have the same value in all the corners, and here we're grouping 1s, you can group the corners. They make a 4 grouping. Right? So the corners touch.
sorry, I thought you were gonna say earlier that, so you can wrap around both top and bottom and right and left.
Right.
Got it. I thought you said what you know.
So what's common to the corners?
Not,
Yeah, not B, not, yeah. Okay. All right, one more. Let's group the zeros.
don't pairs.
What would you do with the don't pairs?
Make the don't pairs just ones. You need the first column and then 2 corners on the bottom.
Does everybody agree? Right, I would make these 1s, because if I would make any of these don't pair 0, I create more groupings, right, which is going to create more terms. So yeah, if I make these don't cares ones, I just got this 4 grouping here and this 2.
That's all left, the bottom, right?
Oh, can you do this? That's a good question. Actually, I think it's only when all the corners are the value you want to group that you can group it. But I mean, even, well, let's see, the other thing is 0 and 10 unit distance. I don't know if 0 and 10 is unit distance. Now, you see, if you look at 0 and 10, they're not unit distance because they're diagonal. So yeah, that would be like doing a diagonal, like somewhere in the middle. So that's a really good question, but yeah, because they're diagonal, it wouldn't work. But you know, if these were ones, you could still group this as 2, you know, or you could group 2 and 10, you know, because those, you know, are rectangular. Okay, but yeah, you couldn't do 0 and 10, even though when the corners, you know, when all 4 corners, you know, you can get a 4 grouping, but you can't do like a 2 grouping diagonal because it's not unit distance that well. But that's a good question. All right, but what would this 4 grouping give us? What term?
Not C.
Not C, not D. Not D, not C, either one. Let's see, so this is not F, it'd be not C, not. And then how about this 2 grouping? What would we get there?
Not B. A, not B, not B.
Okay, so A, not B. Then what was the other one you said?
Not B.
Not, yeah, not D. Yeah, only C drops out, right? Because here it's C, here it's not C, so that one. Okay. All right, so if these examples make sense to you, then the activity that you have should be doable. Now, each table should have one of these activities. Now, there's 8 Carnot maps, but I want you to do 12 reduced expressions. For each Carnot map, I want you to do a reduced SOP for F. So what are you going to circle for reduced SOP for F? You're going to circle ones, right? And for these 4 that are on the right side of the handout, I want you to also do reduced POS for F. So what are you going to circle if you want reduced POS for F? 0, because you want to get the reduced SOP for not F, right? Because then you're going to do the Morgan splice and everything inverts, aims towards aims. Okay. Now, before you start the activity, let me go over lab 1. That way, once I'm done talking about lab 1, you know, you can work on the activities group, and once you're done with that, you can go right into lab 1. Okay. So I want to show you the instructions for lab 1. So it's on Canvas. So wake up my computer. The answers to the activity are up here posted on the wall. And when you look at the answers, what's in red ink, that's the answer for the reduced POS. And then what's not in red are the answers for the reduced SOP. So again, I realize that when I you know, show any of the documents up on the screen here, the resolution's not the best, but I'm more using it as an outline. If you want, you know, more clarity, you can just look at it on your computer. Because again, this is on Canvas. You all now should be aware where the module section is on Canvas because you all submitted your lab 0. But if you haven't spent a lot of time looking at the modules, you know, do so because there's a lot of resources there. Okay. And one of the resources are the lab instructions. Okay. So, you know, if you just go to modules and you go, you know, scroll down some, you'll see like lab 1 instructions, lab 2 instructions, and so on. So in lab 1, we want you to design a lockbox. And the lockbox has 4 inputs. And when the lockbox opens, the output becomes 1. Okay, so when it's unlocked, the output is 1. When it's locked, the output is 0. And the lockbox only opens for these input combinations. Okay. So the first thing we want you to do is make a truth table. So since each input has 4 bits, how many rows are you going to have in your truth table? Right, you're going to have 16 rows instead of 8, right? Lab 0 had 8 rows in the truth table. This time you're going to have 16 because you got 4 inputs instead of 3. So make the truth table based on this statement. And then, just like you did last class and just like you did for lab 0, looking at the truth table, come up with the non-reduced SOP for F and the non-reduced POS for F. All right, so that's just a repeat of what you've done. That's just like, review if you will. After you do that, we want you to draw a black box diagram for this locked box. So what does a black box diagram show us? Like, what's the main reason to even do a black box diagram? What does it show?
Inputs out.
Yeah, it just shows your main inputs and your main outputs. So how many inputs? 4. Now, you're going to see eventually we're going to have 3 outputs. Because notice there's a part 1 and a part 2. But for part 1, we want you to have an output for SOP, the reduced SOP, and also an output for the reduced POS. On Tuesday of next week, next class, we're going to talk about 2 other forms of digital circuitry. One's called NAND, the other's called NOR. And after you know what NOR is, we're going to have you add a 3rd output. Okay, so eventually your black box is going to have 3 outputs, but as far as what you know for today, there's just going to be 2 outputs. One's SOP, one's POS. Okay? Okay, and then we want you to get the reduced SOP and the reduced POS for this locked box. So this is where the K-map comes in. So you're going to have a 16-cell K-map. You're going to take your truth table that you determined earlier, and you're going to transfer those outputs into a 16-cell K-map, and then come up with the reduced SOP for F. So what are you going to group for that? 1s, and then we also want you to get the reduced POS for F. So what are you going to group for that? 0, right? Because you'll get the reduced SOP for not F, and then do the Morgan twice, everything inverts, ands to ors to ands to get the reduced POS. Okay, and then once you have that, now you build it in Vivado using Verilog. So lab 0, you just had 1 Boolean expression, right? And 1 output. Here, you're going to have 2 Boolean expressions, eventually 3. But for right now, since you're just doing POS and SOP, you're going to have 1 Boolean expression for SOP, 1 Boolean expression for POS. So you're going to have 2 outputs. So in your design source, instead of just having 1 assigned statement like you did in lab 0, you're going to have 2 assigned statements, right? 1 line for the POS, 1 line for the SOP. Okay. Since you have 4 inputs, how many switches are you going to need in your constraints file? 4, right? You had 3 last time because you had 3 inputs. Here you got 4. How many LEDs are you going to need for this? 2, right? Because you'll need 1 for POS, you'll need 1 for SOP. Eventually, you'll need a 3rd for NOR. Okay. So today, for part 1, you can't do the entire lab yet. Because like I said, you don't know what NOR is. You'll find out on Tuesday. But if you're able to go all the way through simulation and get a good sim for both SOP and POS before Tuesday of next week, you'll likely finish this lab before you leave on Tuesday. Because if you have part 1 simulating correctly, that's 90% of this lab, right? Because all you'll have to do on Tuesday is add a 3rd output, add a 3rd equation, just modify your constraints to add an LED and, simulate again, make sure the simulation's still good, and then download to your board and you're done. Okay. So that's lab 1. Now, also, I just want to make some general comments especially about troubleshooting, because, over the weekend, I got quite a few emails and believe me, I like getting emails from students. I enjoy that. But I would say probably like maybe 50% of the emails they got, I think if the person had just looked at what's on Canvas, they probably wouldn't have been able to figure it out themselves. They wouldn't have had to wait for me to respond. So on Canvas, besides these lab instructions, there's a document, general troubleshooting. Okay, so like I said on the first day of class, any type of design class, when you do any kind of design, the chances are it's not going to work the first time. There's going to be something wrong. And I totally understand you're totally new to this software. So when something doesn't work, you're like, oh, what do I do? Well, the steps are here where if your design doesn't simulate correctly, right? Because that's always the first thing you should try to do, right? You want to simulate before you even think about downloading to the board. Don't download to the board until you have a good simulation. If your simulation is not correct, the error is either in your design source or your sim file, or it could be both. And if you have either blue or red in your timing diagram, like either an output or input is blue or red, that usually means that something's not declared right, like you don't have an input or output declared right, or something's not connected right. Often in the sim file, after you put your file under test and you put UUT and then you start going dot, input or output name from your design source, and then in parentheses, whatever you called your input or output for your sim file. Well, if something there is not right, then that input or output, it's not being connected to the simulator. And that can cause like a blue or red. Okay, there can be other things that can do it too, but that's like the most common. So, if you're not getting a good simulation, look at your design source, look at your sim file. Now, if you have a good simulation, your waveforms are green and you've also checked the data and it matches your truth table, but then it fails when you try to implement or generate a bit stream so you can download to the board, that's usually a constraints problem, okay? The other thing is, and I find this annoying and I find this frustrating because it's been like this forever. I mean, when I was an undergrad student, it was the same way. Compiler errors or the warnings, the messages are usually useless. Okay, they're usually cryptic. You look at it and you're like, what are they talking about? And I'm the same way. I look at them and I'm like, I don't know what they're talking about. But what can be useful with those error or warning messages is often they'll have a link. Sometimes it's at the very bottom of the message and, it'll be blue. And if you click on that link, it will take you to the part of the code, the file and the part of the code where it doesn't like something. Now, what it doesn't like is not always right on that line it takes you to, but it's usually close to it somewhere. Okay, so at least it narrows it down somewhat for you. Okay, I wish they made compilers where it said, this is the issue. Yeah, that would be great, but they just don't do that, okay, for whatever reason. Okay, the other thing is sometimes like an error or a warning, it won't have a link, but it will have like a path, like a file path name to like a log file, or it will tell you to type something in the window, the TCL message window. And a lot of times, not all the time, but a lot of times that log file or what you type in will provide more information that sometimes is more useful, like it's more descriptive of what it doesn't like. Okay, so those are just some things, that you can look at. And by all means, if you're troubleshooting and you're following the steps and you're still having difficulty, I mean, contact me. But when you contact me, tell me what you've done. Say like, okay, Gary, I got a good simulation. I checked my simulation. The waveforms are all green. I checked the data. It matches with my truth table. But now when I try to implement or I try to generate a bit stream, this error is coming up. And, I checked this line because, I clicked on the link. It took me to that line, but I still couldn't find, what the issue is. Okay. Because, when I get an email, it just says, Gary, my design doesn't work. The first thing I write back is I go, was your simulation successful? Okay. If yes, and I just go through what I just told you. All right. And most of what I just told you is also under this general troubleshooting. Now, when we get to you know, later on in the quarter, when we get designs that are a little bit more challenging, or actually a lot more challenging than what we've done thus far, there's additional troubleshooting steps you can do that I'll talk about then. In fact, there's a video that Dr. Benson made that's, you know, goes into more like sophisticated troubleshooting that you can do in Bavad. Okay, but, you know, you won't need that yet. Okay? All right, so do you have any questions before you start your activity today? And then after that, you can start into lab one. Again, once you get to the lab, if you want to go somewhere else to work on it, that's fine. But make sure before you leave, if you do leave, that your group turns in the activity, right? Because again, if you're not here for the activity, you don't get credit for it.
So we're doing, you said you're doing the SOP for the left half, or go for the right half?
You want to do reduced SOP for all 8, and then just do reduced POS for the 4 on the right. So there's a total of 12. Okay. Also, in about 10 minutes,